power rule for derivatives and differentiability. Rewinding just a little bit, this is what we did Monday. That's the definition of a derivative. Today we're going to learn a shortcut. Let me warn you though, this is not one of those places where once you learn the shortcut you never have to use this. AP loves to ask questions and phrase them in a certain way and give you the right information that forces you to know about that definition. So we won't use it often, but because it's so foundational, we'll keep coming back to it occasionally and making sure you remember it. Okay, this was amazing. We did a lot of great things with that, but goodness, here's the example. We're not going to walk through this, but if you wanted to find the derivative of an x cubed, then you'd have to find f of x plus h, which means all of those would need an x plus h in them, which it's already done for us. We're not going to do this. It would be right there. That's really crazy. But we can kind of remind ourselves what's going on here. There's f of x all over h. So you cube it out, you square it out, collect like terms. You've got this giant mess on your hands. Then the mess cleans up a little bit because a bunch of things cancel out. You can factor out the h and cancel it out. Anyway, eventually you get down to that. That's just, it's doable. Like, you're all capable of doing that. We're never going to ask you to do that because it takes too long. So, you might disagree with this characterization. This is beautiful. Like, is it? But it is definitely very tedious. And that was just a cubic. So what in the world, if you had a 5th degree or a 9th degree, that would be awful and time consuming. But there's a pattern that happens. And let's back up a little bit here. F of x was x cubed minus 7x squared plus 3x minus 12. So did we learn the shortcut last year at the end of pre-cal? So we're not relying on anyone's observational powers. We're more relying on their memorizing power. Not memorizing, just understanding what it was. So from last year or from the pattern here, do you remember what the derivative of g would be? Wait, what's 9 times 7? 63. You had the x to the 8th right. And then what's the second term? 6 times 8 is 48. X to the 3rd. Right, bring the power down and decrease it by 1. And that's why that would be an 8. That's why y'all are whispering. 63x to the 8. I can multiply 9 and 7, but I can't subtract 1. I deserve to give myself the stamp of shame there. Calculus is easy, algebra is hard. Yes, sir.
How did negative 12 go to 3?
Someone want to answer that? The question is, what happened to the negative 12? It didn't go to 3.
Yeah, that's right.
It's okay. It went to 0. Yeah. Okay, so there's the power rule in the shortcut form. All right, the n goes to the front and decreases by 1. Power to front and decrease the power by 1. Today is a day, I used the stamp on myself a minute ago, but today's a great day for that stamp because this rule is the calculus thing. That's pretty easy, like multiplying numbers, subtracting 1. Got it. But we're going to get to some algebra things later that make us do some algebra at the beginning and at the end that make it a little bit harder. So number 1, let's see, let's just pick on somebody. You know what, let's pick on 3 people. That way we can get through more popsicle sticks. That's what makes a good day for me. More popsicle sticks, the better. So one piece at a time. Justin, what's the derivative of x squared?
2x.
Good. And Brooke, what's the derivative of 3x? And Ava, what's the derivative of minus 8? 0. So pretty easy when they're in that form. Number 2, find the slope of the line tangent to the graph. Well, that's a lot of words to say g prime. And you'll notice on this sheet we try to use all the different phrases, but they all mean find the derivative. So the derivative of 5x to the 9th, Abby, what would that be? 45x to the 8th. Number 3, instantaneous rate of change. Well, again, that's just a fancy name for a derivative. And I get to pick 5 popsicle sticks for this one. That's a good day. Holly went fancy and wrote her name on the other end of the stick. There we go. So, Avery, derivative of negative 2x to the 7th? Negative 14x to the 6th. Jake, the derivative of 5x to the 5th? 25x to the 4th. Trying to make them line up, but I can't write that small. Holly, how about the derivative of negative 3x squared? Negative 6x. Ashlyn, derivative of 17x? 17. And Jimmy, the derivative of negative 20? 0. You can put the plus 0 or you don't need to, whichever. Okay, that's the easy part. Now for the algebra stuff, number 4, d dx. Remember that just means take a derivative. But I can't really use the power rule unless my x's have powers. So let's use our algebra skills first, so no derivatives yet. Let's change the cube root of x into, how could I write that as x to a power? There we go, x to the 1/3. What about 5 over x cubed? 5x to the negative 3. And then what about the 5th root of x squared in the denominator? What will that power be? Negative 2/5, right? The power is 2, the root is 5, and it's in the bottom, so negative 2/5. Be careful though. Are we done with this problem? No, that was like the algebra step. Now we need to actually take a derivative. So the rules are the same. The numbers are a little harder, but 1/3 x. Oh, here's where I should pull popsicle sticks and put people on the spot for their fraction abilities. What's 1/3 minus 1? Negative 2/3. Let's see, negative 3 times negative 5 would be plus 15. What's negative 3 minus 1? Negative 4, although be careful, plenty of people will put negative 2 there. They think, oh, just make the number go down. I mean, that's right, make the number go down, but if you're negative, you get more negative. And then that last one, 7 times 2/5 would be 14/5. Negative 7/5. And that is definitely a safe stop. I mean, you could write it differently if you wanted to, but there's really no reason to. I mean, I guess a multiple choice might change them all back, but no way you would do this on your own. I mean, not that you couldn't, you just wouldn't. Not that we're going to see it. So yeah, I'm not even boxing that up. I would definitely do the safe stop and not mess with accidentally making some mistake. I'm like trying to double check and make sure I didn't mess anything up. No, I think that's right. But yeah, safe stop though. Number 5, you can't take a derivative of the top and the derivative of the bottom separately. It would be really nice if you could, but there's a separate rule for that. That's called the quotient rule. We'll get to that on Wednesday. So I can't take the derivative of the top and the derivative of the bottom separately. That'd be nice, but it doesn't work that way. So I've got to do an algebra step. Let's divide all of those by x squared. So some of them are easy. 2x squared minus 3x plus 9. Got it. That's the easy part. What about negative 7x over x squared? What does that reduce to? Let's do it that way. You could do negative 7 over x. That would be true, but I want a power, so let's do minus 7x to the negative 1. That's the same thing as 7 over x, but I can't take a derivative of 7 over x yet. So let's make it x to the negative 1. And same thing with this last one. I could write 1 over x squared, but I can't really take a derivative of 1 over x squared. So let's write it as x to the negative 2. Algebra step. Then we can find the derivative. Why not? Let's do 5 more popsicle sticks. Make sure everybody's on the same page, rolling along here. Okay. So, Christina, what's the derivative of 2x squared? Excuse me. 4x, good. Johnny, how about the derivative of negative 3x? Negative 3. Dylan, how about the derivative of 9? 0. I'm going to put plus 0 to kind of hold the spot and show the pieces. Obviously, you don't have to write plus 0. Jace, getting a little harder here. What's the derivative of negative 7x to the negative 1?
7x to the negative 2.
Good, 7x to the negative 2. And Ambria, the derivative of x to the negative 2?
Negative 2x minus 3.
Yes. Very good. And again, do you want to get a common denominator and add all? No, you do not. Right? Safe stop. And again, the 0, it doesn't need to be there, but it's not wrong if it is there. And so, initially, anyway, I will see students put the 0 in there because it just sort of helps them remember that, that's right, the derivative of a constant goes away. And so if it helps you kind of keep track with the terms, by all means, put a 0 in there. All right, number 6. Another one with algebra first. Cube root of x in the bottom. So, Ben, put Ben on the spot here. How could I rewrite the cube root of x in the denominator as x to a power? Perfect. X to the negative 1/3. And then I'm not done. That's just the algebra step. Next is taking the derivative of that. So, Caden, help me out. What's the derivative of negative 3x to the negative 1/3?
1x to the negative 3.
Good. That's what's up. Yeah. Okay, so the power rule is easy. The only hard part is making sure you get your powers and roots and division, all your algebra steps correct. Okay, differentiability. We've been taking derivatives. Differentiability is a fancier name for derivative, basically. A function is differentiable at a point if the derivative of the function exists at the point. So, if the slope at a point exists, slope at a point, that's basically what derivative is. If you'll keep those two things like linked in your brain, most of first semester of calculus will make sense. And certainly when it comes to these special weird cases, like when is it not differentiable? So can you think of examples of like graphs you've seen where you couldn't really take the slope at a point? A hole. That's a specific case of if f has a discontinuity at x equals a. There were 3 types of discontinuities. Hole was one of them. What were the other types? Jump. And infinite or vertical asymptote. So if any of those things happen, you can't have a slope at a point if there's not a point there. That was the hole. You can't have a slope at a point if there's a jump. And you can't have a slope at a point, well, vertical asymptote would mean there's nothing at that point anyway. So if one of those things happen, you definitely can't have a slope. Now the other two examples of not differentiable are a little bit trickier. You think of any graphs that they don't have a hole or a jump or a vertical asymptote, but where it would be impossible to take a derivative at a certain spot?
If it has a cusp.
A cusp. You've had these notes before. No? Well, you were in BC, or was it? Did we did this far last year as well? Cusp. I'm going to put that as 3. I guess it doesn't really matter. F has a cusp. Remember, that's the same thing as a sharp turn or a corner. Let's see, what would be an example? Absolute value would definitely be an example. So there's a weird looking graph. There's a cusp, and there's a cusp. A sharp turn. A smooth turn is okay. So like that derivative is fine. But those sharp turns, think about drawing a tangent line. You can't draw a tangent line when it's like a seesaw, right? You wouldn't know how to put that. Lastly, this one's, I think, the trickiest, it's not tricky when you see it, it's the one that people forget. If f has a vertical tangent line, so the other two don't have tangent lines at all. This one has a tangent line, but a vertical tangent line. That's not a good picture of the cube root graph. What's the slope of a vertical line? Slope of a vertical line? It's not 0. That one's 0, horizontal 0. It's undefined. So it kind of makes sense that if the slope is undefined, then the derivative is undefined, because slope and derivative go together. So if there's no point at all, then there's no slope there, no derivative there. If you couldn't draw a tangent line, then there's no derivative there. And then if there is a tangent line, but its slope is undefined, then that means the derivative is undefined, so it doesn't have a derivative either. Okay, some examples. State the values at which f is not differentiable. Well, right away I see a denominator. X can't be -3. That would mess the thing up. So it's not differentiable at x equals 3. And with a little more work, we could determine whether that's a hole or a vertical asymptote, but it doesn't really matter because either one is not differentiable. Can you tell by looking? Is that going to be a hole or a vertical asymptote? A hole, because the top would factor and then they'd cancel, and that puts a hole. But that's 2 or 3 steps down the road that we don't even need to get to. If the function doesn't exist there, then it can't have a derivative there. All right, number 2. That's weird looking. Absolute value. Usually we think of absolute value as just the v. So yes, we're worried about a cusp. The cusp happens when the inside is equal to 0. So I think this one might have 2 cusps. Which is weird. But if the inside is 0, that's where it does the bounce thing, and a bounce might mean, or does mean, there's a cusp. So x minus 3 and x minus 2. So it's not differentiable at 3 and 2. And what that graph would look like, roughly, so normally there's our graph, but that absolute value bounces the negative up into the positive, and so we've got a cusp at those 2 spots. But the main thing on that one is the insides of an absolute value, wherever there's 0, that's where it's bouncing, and not like smooth bouncing, like cusp bouncing. Number 3, find the values at which that is not differentiable. But that looks fine, like that's continuous. There's nothing, especially if you think about the graph of a cube root. That looks nice and smooth. So let's take a derivative and see what happens. The others I didn't have to get to this step, but that graph looks okay. So h prime then is 1/3 x to the negative 2/3. But that negative is what has me worried, because that sends it to the bottom. Oops. So now what's the problem? What value of x would be a problem for that derivative? 0. X can't be 0. So at x equals 0, the slope is undefined, which matches our picture if we drew it well. So it's not differentiable at x equals 0. So that one's kind of weird, because you may not know that unless you really know the graph well, or you actually take a derivative. The others you can tell before you take a derivative. Number 4, people will miss this on the test, and it's so frustrating. State the values of x at which that thing is not differentiable. Let's see. Ooh, negative x to the 5th. So, like, who knows what this thing is doing? Something like that. Thinking back to pre-cal and algebra 2, lead terms negative, and it's x to the 5th. But that doesn't really matter. It's always differentiable. Always differentiable. Because polynomials are continuous and differentiable everywhere. And we use that a lot, because a lot of times we need a function to be continuous in order to use IVT or squeeze theorem. Those are 2 that we've done. Later on, we'll need things to be differentiable to use other theorems, which is why we like polynomials, because they're always both of those things, so we don't have to worry about it. But in this section of the test, people are going to get so focused on finding places where it doesn't work, they're going to do something weird with this instead of recognizing that it's a trick question. It's always continuous. It's a trick question because it's easy, not because it's hard. Okay, number 5. Let f of x piecewise function. Which of the following statements are true? The limit exists, it's continuous, it's differentiable. Okay, to check the limit, What am I going to need to do to see if the limit exists? Yeah, the left and the right. So I need a left limit. See if that equals the right limit. So the left limit would be the x plus 2, and we're a little less than 3. So 3 plus 2 is 5. The right limit would be when we're greater than 3, or x minus 7. So I plug in 3. 12 minus 7 is 5. So we're good with statement number 1. Yes. For continuity, I need to add one more statement, f of 3. A little side note after grading the test. For continuity, you have to say left limit equals right limit equals f of 3. And you could write it like this, like some of you did. It's even better if you put the official looking notation on there, which is what most of you did. I let it go if you told me what you were doing, but what I did not give full credit for was if you left off those labels and you did the left limit and the right limit, but if you didn't tell me what they are, then I knew what you were doing, but I didn't give you full credit. This one's multiple choice, so it's a little less formal. But if it asks for a proof, you've got to do left limit equals right limit equals function value. F of 3, that would again be x plus 2, which is 5. So we're good on the first two for sure. Thoughts on how we'll get number 3? How we'll test to see if it's differentiable at 3? So like it's continuous, I know that much. So at least they're touching. There's not a jump there. But what am I worried about for differentiability? It's not a hole because we filled the hole in. Like it's just, this thing is continuous. A cusp. Vertical asymptotes is like when the bottom's there, so no vertical asymptotes. But maybe a cusp. So they connect, but like do they connect smoothly or do they connect at a corner? So I need basically the derivative of each side. I need the left derivative and the right derivative. So it's similar to that function checking. You got to check the left side and the right side to see if they meet. Now I need to check the left slope and the right slope to see if they have the same slope. So the left slope, the derivative of x plus 2 would be 1. The right slope, that derivative is 4. Those don't equal each other, which I guess makes sense. So this thing has a slope of 1, and then it has a slope of 4 where they meet. So there is a cusp there. So 1 and 2 only. The trick on this one that we like to do to people is make the derivatives equal, but it not be continuous. So if people skip that step, graphically what that means is they have the same slope. And so if the only thing you do is check their derivatives, you're like, oh, that's a slope of 1/2 and that's a slope of 1/2. It must have a derivative. Like, well, no, because it has to be continuous before you check the derivative. So you can't just jump to left slope equals right slope. You got to make sure it's continuous and then check the slopes. Number 6, the graph of a function shown on the right, at which value of x is f continuous but not differentiable? Continuous but not differentiable. A. Definitely A. Let's see, B is not even continuous. C is continuous and differentiable. D is not differentiable but also not continuous. And E is continuous and differentiable. Like there's slopes at C and E, so we're good with those. So yeah, that one was A because of the cusp. 7, similar looking question anyway. The graph of the function shown on the right of the following intervals, so not a point, but an interval, on which is f continuous but not differentiable. So, one at a time here. 0 to 1. There's nothing weird going on 0 to 1, so that is continuous and differentiable. From 1 to 2, there's a hole there, so it is not continuous, which means it's not differentiable. Yeah, if you're not continuous, you can't be differentiable. From 2 to 3, let's see, it is continuous, but there's a cusp there. So I think we found our spot. Found our answer. From 3 to 4, we'll just check. 3 to 4, that's not continuous. And if it's not continuous, it is definitely not differentiable. Number 8, function given by, it's piecewise. At 3, undefined. It's definitely not undefined because there's an x equals 3. And then we're looking at continuous versus differentiable. One of those I could rule out without testing anything. One of those answer choices I can definitely rule out. Right, that's impossible. You can't be differentiable but not continuous. Like if it's differentiable, it has to be continuous. So now I'm looking for continuous. I'm still looking the same thing. So continuity is left limit equals right limit equals function value. So we plug in 3 to the left, we get 9. That would be this one, the left limit. For the right limit, we're a little more than 3. 18 minus 9 is 9, so we're good there. And for the function value, we're also at 6x minus 9. So we are continuous. So yes to continuous. And then the next thing I need is the slope one. I need the left slope, or the left derivative, to equal the right derivative. The left slope equals the right slope. That's my differentiability test. So it's similar to continuity, except instead of values matching up, we now need the slopes to match up. So the left slope would be 2x, but when I plug in 3, I would get 6. The right slope, the derivative of 6x minus 9 is 6, and those are equal. So they meet up, they're continuous, and their slope is the same, so it is differentiable. It's a lot of work to answer one of those type questions. If we wanted to try to draw it, we know what a parabola looks like. But when it gets to 3, it stops being a parabola and starts being a line. But it's like a smooth transition. So the derivative there exists. They're connected, continuity, and it's a smooth transition. The slope's the same. There's no cusp there. The function absolute value. Oh, this should be an easy one if we draw the graph. Let's go 3 more here and then we'll be done with notes. Austin, Lexi, and James. Oh, but we still see the graph there. Austin, is f continuous at x equals 0?
Yes.
Yes. Lexi, is f differentiable at x equals 0? Why not? There's a cusp there. James, I guess that's on there just to give us 3 topics or 3 choices here. Is f defined at x equals 0? Yeah, there's a point there. So which of the following is true? 1 and 3 are true. Alright. So, a little bit of concept stuff about continuity versus differentiability, and a whole lot of algebra stuff on worksheet 2. So assignment today is worksheet 2. Tomorrow I'll give your test back. We'll have a little more time. We still have, we don't have much time left. 7 or 8 minutes left.